Okay, so hi everyone. In today's lecture, we will continue with the last lecture that we have started on link analysis. And today we will discuss three important concepts. One is page rank, which we have already discussed in, I think, 2-3 lectures back. We will try to mathematically formulate it and see why page rank is so efficient. We'll also discuss the limitations of page rank, right? And later after that, we'll see how those limitations will be tackled, addressed using another ranking algorithm called div rank. Okay, and then we will discuss something called sim rank. Okay, so page rank, div rank, and sim rank. These three ranking algorithms we will discuss in today's lecture. Okay, so the intuition of page rank we have already discussed before. So the idea is that page rank tries to model how web surfing behavior happens, right? For example, you are currently browsing a particular web page. You are looking at a particular web page. Now at that time, what would be your decision? Would you follow one of the hyperlinks that are present on the web page and then move to another hyperlink, move to another page? For example, say you are on web page A. So you can take three decisions, right? One decision is that either you move through this link and you open web page B, or you move through this link, you open web page E, or you suddenly type a completely different web page whose hyperlink is not there on the web page A, right? And so let's assume that you type the URL of web page F and you open and then you open this web page, right? So you see there are two decisions. One decision is whether we follow any of the outgoing hyperlinks that are present on the web page and move to the subsequent page, or you just randomly open another randomly type another URL, another link, and open another web page. These are the two decisions, right? You choose either of them. So let's assume that let's for the time being, let's assume that you only choose, you only consider the first decision. And what's the first decision? You basically choose a particular hyperlink and move through the hyperlink and to open another web page, right? So let's assume that let's define two quantities. One is called FW. FW is the the set of nodes that the particular web page W points to, or the particular node W points to. So basically this is W, and right, these three nodes basically form FW. Okay, forward neighbors. Okay, forward neighbors. Let's define another quantity which is called BW, which is, so BW consists of backward neighbors. So those nodes which are pointing to W. Okay, BW backward neighbors, FW forward neighbors. Okay, so now this is very intuitive that the rank. So if we just follow hyperlinks and then keep moving from one hyperlink to one page to another another page through hyperlink, right? In order to quantify the impact of a page W, right? So impact of a page or rank of a page W, RW, is defined by all the outward all the backward neighbors, right, which are pointing to W, so BW, right? Now we basically look at the impact of all each of these backward neighbors. Okay, say for example this node has some impact. Say let's say the impact is 5, let's say. Okay, and this node has, let's say, 3 forward links, right? So say this node is B, right? So if B mod of FB, the size of forward link is 3. Okay, So now when the importance of this node is distributed, right? We assume that it is distributed uniformly, right? Uniformly based on the forward links. So 5 by 3 amount of importance would be forwarded through each of these forwarded links, each of these forward links. Okay, so 5 by 3 here, 5 by 3 here, and 5 by 3 here. Okay, similarly, say for this node, let's assume that this node has 2 forward links, and the impact of this node is 4. Total impact is 4. So it means that 4 by 2 will be moved through this, 4 by 2 will be moved through this, right, and so on. So the impact of W is nothing but the partial impact or the proportional impact of its backward nodes, right? So the impact of W is sum of the proportional impact of this plus this plus this, and this proportion is calculated based on the forward links. Okay, so this is the computation. So the computation, so the impact of W is nothing but the sum of all each of these backward nodes, impact of the backward node divided by the neighbor, right? I mean, you can instead of writing in, so NB is already defined. NB is basically mod of FW, right? FB, right? So this would be mod of FB. Okay, now this is clear. Now through this, if the network is connected, then you can measure the importance of nodes accordingly. Now, what's the problem here? The problem here is that let's say there is a node, okay, which is not connected to any of the hyperlinks. It may happen. Say I have created a web page, and the web page doesn't have any hyperlink, and none of the web pages on the World Wide Web point to this node, point to my web page. So this has become an isolated node, right? Now for the isolated node, how do you compute the impact based on this? You can't do it, right? So therefore, what was proposed is the second option, the second decision that I mentioned earlier, that instead of just following the hyperlink, there is certain probability that you open a random web page, right? There is certain probability that my web page, which is not pointing to any web page, which is also not pointed by any other web pages, my web page will be suddenly opened by somebody, right? And I will get some prestige. Okay, now this is the second decision. Now, what is this probability? Now, let's assume that all the nodes or all the web pages on the internet, they are equally likely to be open by somebody, right? To be browsed by somebody. So the probability is uniform probability, which is 1 by n. N is the number of nodes present here. Okay. So now here's an example, numerical example, as you see. So so you see here, node A has got impact of 1, 2, and 3. So 1 plus 1 plus 1, 3. And then this 3 impact is now divided through these 3 hyperlinks, 1 by 3, 1 by 3, 1 by 3. Okay, similarly for this one, and similarly for this one. Okay. Right, I think there is some issue here, so some mistakes here, but I hope you understand the problem. So now the problem is, now this is this web surfing behavior can be easily modeled using something called random walk. Okay, now what is random walk? So random walk is a very interesting concept in mathematics, right? Which basically says that let's assume that there is a walker or a person who is drunk. Okay, so the person doesn't know how to move. Okay, so what he does, he basically follows any path and starts moving. Okay, he follows any path and starts moving because he doesn't know where to go. He's a drunk person, so he basically follow any path and he follows any path and move. So and and say let's assume that a random walker, the random walk starts at a particular at a particular web page. So what are the possible paths? The paths are basically hyperlinks. So the the walker actually would follow any of these hyperlinks. Okay, and we assume that all these hyperlinks are equally likely, right? Therefore the impact is distributed equally, right? There is no bias as such. It is not the case that okay, this link will be highly likely to follow compared to these things. It's not the case. So it's a pure unbiased random walk. We can also make it biased. Okay, it's a pure unbiased random walk. So in random walk, the idea is either you follow any, particularly PageRank, there are two ways. Either the random walk follows any of the hyperlinks, or the random walk jumps from this node to any of the other nodes. Okay, so you may wonder that why this jumping is important. I told earlier that for isolated nodes it's important. Now also let's consider two other scenarios. So one is called dead end, right? So let's assume that random walker currently is at this node, and the next stage he moves to this node, okay, through this link. Okay, now when the random walker is here, what would be the next destination? This node doesn't have any outer links, so this is called dead end. So you are stuck here. So when you do this iterative way of updating things, I will discuss how you are stuck here. You won't be able to move further. This is called dead end, right? There is also another phenomena called spider trap. What is spider trap? Let's assume that you are currently at this node, okay, the random walker. So the random walker, what he would do, he would move through this link, okay, then from this to this, from this to this, this to this, and this to this. So he keeps on looping around these three nodes again and again. So this is called spider trap. So when a random walker gets trapped into dead end or spider trap, he gets stuck, right? So if the random walker only follows the hyperlink for movement, right? If the random walker doesn't know how to jump from one node to another node, right? Jump means without any hyperlink, how a random walker jumps from one node to a node which is far away from the given node. So if he doesn't know, then he would get stuck here. Okay. So to overcome the problem, what was proposed is that random jump is that say let's assume that at this node, at every node, okay, at every node there are two probabilities. Either you follow one of the hyperlinks, or you move from this node to any of the nodes. So when the random walker is at this node, he can easily move to any other nodes with that probability, with the second probability, which is 1 by n, as I mentioned. Similarly, when he traps here within the spider trap, there is some probability, non-negligible probability, that the random walker can get out of this spider trap and moves to some other node. Okay, so this is the idea. So you see that PageRank can be intuitively thought of a process, of a random walk process, where two interesting phenomena are happening. One is the random walk is happening through hyperlink, and random walk is happening through a random jump from one node to any other node, irrespective of whether these two nodes are connected or not, right? You can also model web browsing through PageRank. Okay, so now let's look at these two probabilities very clearly. So this probabilities, this component is something that we have discussed already. So what we are calculating, again, we are calculating the importance of page jump. Okay, it is the proportionate sum of the proportionate importance of all the backward nodes, right? Normalized by the, that's why I'm saying that proportional, because this is normalized. Okay, now what is this factor? This factor is 1 by n. So this is the ultimate formula of PageRank. You see this component, you see another component, and these two things are parameterized by alpha. Okay, so you may want to give more weightage to this. So automatically the weightage of this component will be reduced. You may want to give more weightage to this will be reduced, right? So this component 1 by n, this is called teleportation probability. Teleportation probability, right? So the teleportation probability is a very interesting way to connect any network, irrespective of whether the network is connected or not. Let's assume that there is a network of 10 nodes and none of these nodes are connected. Okay, so if you want to do random walk, how do you do that? There is no hyperlink. So through the teleportation probability, you can say that, okay, there is some probability through which I can jump from one node to another node where these two nodes may not be connected. Okay, so and I discussed this alpha. This alpha parameter is called damping factor. Okay. Okay. So alpha is not exactly called damping factor. What is damping factor is 1 minus alpha, right? Which is called D. It doesn't matter. I mean, 1 minus alpha is damping factor, meaning that alpha can also be called as a damping factor. But anyways, 1 minus alpha is called damping factor. So this is set to 0.85 generally. Okay, but you can choose again depending upon your so D is set to 0.70 to 0.85, but depending upon the situation, you can also change it. Now, what we also do at every stage, right? When you compute page rank of a particular page, right? We also need to make sure that the sum of all page ranks, sum of page rank values of all the nodes would be 1. Okay. So when we do the so you see here, this is a recursive formula, right? You see RW is dependent on RB, right? So if you write it in a matrix form, can someone tell me how do you write it in a matrix form? So you can write in this way. Say R equals to say R, I plus 1. I plus 1 is the iteration is now what is this? What is this component? What is this component? How do you capture this component? Summation on B 1 by NB. How do you capture this? This can be, what is NB? NB is the number of forward links, right? You can easily capture this using adjacency matrix. Let's assume that you have an adjacency matrix A where Aij is 1 if I is connected to J, if there is a directed link from I to J. Okay, otherwise 0. Right? So in this matrix, right, think of this. So this is I, okay, and so this is I. This row corresponds to I, and you have some 1, some 0, 0, some 1. Okay, so the sum of this row would indicate what? The sum of this row indicate the number of forward links. The sum of this one would be 3, which is nothing but Fi mod, number of nodes which node I is pointing to, isn't it? Right? So if you divide each entry by Fi, okay, so ith entry is divided by Fi, right? So you can get this entry very easily. So this is called row normalized adjacency matrix. Row normalized adjacency matrix, so that the sum of elements of a row would be 1. So what I'm doing, I'm taking the summation of all the values in a particular row and divide all the elements of that row by their sum. Similarly, for jth entry, take the sum of all elements and divide each element by the sum, so that when I take the sum, the resultant sum, it would be 1. Okay. Now this kind of matrix is called stochastic matrix. Okay, it's a row normalized. You can also make it column normalized depending upon how you want to write the adjacency matrix. So this is stochastic matrix. So this is, so let's assume that you have A, and A is a stochastic matrix. A is a stochastic matrix, right? So this element can be captured using A. So therefore you have A, right? And 1 minus alpha is definitely there. So 1 minus alpha A, and what else is there? You also have RB. RB is essentially, so when you represent everything through a matrix, right? RW and RB are two elements of the matrix R, right? So this would be R plus alpha. Now this is Ri. Why this is Ri? Because at ith iter, at whatever value is there, think about it. Let's look at this node, okay? At ith iteration, you know the impact of these neighbors. So when you want to update the impact of this node at I plus 1th time, you take into account the impact of its neighbors at ith time, right? Okay. So this would be Ri plus alpha. Now this is the alpha, and 1 by n can, so 1 by n corresponds to each of the nodes. As I mentioned, at every node there are two probabilities. One probability indicates the teleportation probability, 1 by n. Other probability indicates whether to choose the particular link or not. Okay. So 1 by n can easily be captured again using another matrix E, right, whose dimension is V mod V, and each of these entries is 1 by n, 1 by n, 1 by n, dot 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 1 by n, right? So this is E, right? So let me write it afresh. So the matrix formulation would be R. R is a page rank matrix of size V cross 1, mod V cross 1, right? So this matrix is getting updated at every iteration. This is 1 minus alpha R I A plus alpha E. Okay. And E is again a V cross 1 matrix with where each entry is 1 by n. Now it's a V cross 1 or 1 cross B. You just adjust it depending upon the dimension. Okay. Now this is the matrix. This is the closed form. This is the closed form recursive formulation. So how do we start page rank formulation? How do you start page rank computation? So we know A is static because this is on static network. We know A. So in order to calculate R1, let's assume that I equals to 0, right? So at I equals to 1, so at R1 this would be 1 minus alpha R0A when I equals to 0 plus alpha E. What is R0? R0 is the page rank value at I equals to 0. So let's assume that at the beginning, when you start the calculation, the page rank value of all the nodes is equal, same, 1 by n. Okay. Why 1 by n? Because it is also important that the sum of page rank would be 1. So let's assume that everything is 1 by n. So you start with 1 by n, and then you get R1. Then you use R1 to get R2. You use R2 to get R3, and so on and so forth. Okay. Alpha is fixed. E is fixed. The changing factor is R0I, Ri and Ri plus 1. Okay. How do you stop? You stop when you see that at two subsequent iterations, say at t and t plus 1, Rt and Rt plus 1, the elements of the matrix R do not change much. Okay. So you set a threshold that, okay, I stop when I don't see any much change, right? For any further change in the values of R, then you stop. Okay. Now this is page rank. So in the book, you will see that an example of page rank calculation is also given. So you can refer to this for more discussions. Okay. Now here, another interesting trick you can do here. So in the teleportation probability 1 by n, right? I mentioned that we assumed all the nodes are equally likely. Okay, so you may, in some cases, you also want that you may want that, no, I don't want all the nodes to be equally likely. I want 20% of the node, or I want only this set of nodes, say node 1, 5, 8, 12. Only these 4 nodes to be equally likely, and other nodes preference would be 0. Right? So what I mean to say is that at every node, I mentioned earlier that there is a teleportation probability of 1 by n. That means that you can jump from this node to any of the nodes in the network. Okay. Now what I'm saying is that I would not let the random walker jump to any of the nodes. I would only allow the random walker jump to a fixed set of nodes which I want to fix beforehand. Okay. So only for those nodes, the probability would be uniform. For other nodes, the probability is 0. You can also do that. So for that, what you need to do, that this E matrix that I mentioned earlier, all the entries were 1 by n. Now you said that, okay, for say let's assume that there are 6 nodes in the network, and I want that node 2 will be visited, node 2 and node 4 would be visited, would be considered for random jump, right? Other nodes will not be considered. So for these 2 cases, we assume 1 by 2, 1 by 2, for other 0, 0, 0. Okay, these 2 nodes are fixed beforehand. Now this is called personalized page rank. In personalized page rank, you first identify the nodes which you always to which you always want your random walker to jump. Okay, instead of jumping to any nodes, you want the random walker to jump to only these 2 nodes, only these 3 nodes, right? But again, equally likely. But you can also make it non-uniform. You can say that, okay, the probability to jump to node 2 is 3 by 4, whereas this probability is 1 by 4. You can also do that. Now this is called personalized page rank. This is also called topic sensitive page rank. Topic sensitive page rank means I start by identifying some of the topics, right? And now what do you mean by topic? Say for example, on World Wide Web, I identify some of the pages of topic X, right? Let's say some of the pages of topic related to climate change, for example. So what you do, you want your algorithm, your random walker only to move to those pages where the topics are related to climate change. Okay, so but please remember, there are 2 components. The first component remains same. The first component still says that you jump through any of the hyperlinks. The second component says that you jump. I mean, when you do not want to follow any hyperlinks, you can jump, but you can't jump to any of the nodes. You can only jump to some of the nodes which are fixed beforehand. Okay, this is called personalized page rank. Another constrained version of personalized page rank is called random walk with restart. With restart, what does it mean? It means that, say again, you are following the random walk process. Okay, so say let's say you start from here. So this is your seed node. Okay, so first what you want to do, you basically want to you want to follow any of the hyperlinks, right? So let's say you follow this hyperlink, right? Now from every node, at every node there are 2 cases. One decision is that either you move to the hyperlink. The second decision is that if you jump, you are only allowed to jump to the seed node only, right? Now this is the seed node, initial node. When you are at this node, right, either you can jump, you can follow this hyperlink, or you can follow this hyperlink. If you do not follow the hyperlink, if you want to jump, you are not allowed to jump to any node. You are only allowed to jump to the initial. This is called random walk with restart. Meaning you do random walk, but when you want to jump, you restart from the beginning. Okay. Now, the same thing? How do you modify your E matrix? Now only the entry corresponding to this node would be 1, and all the other entries would be 0. Because whenever you want to jump, you can only jump to the seed node, initial node. So in that case, so let's assume that this is node 0, right? So this would be 1, all other nodes would be 0, 0, 0. Okay. Now these concepts are occasionally used in so network science in general. So please remember these concepts. Okay, we'll discuss later when we'll discuss about node to wake, right? Deep walk. We'll discuss random walk with restart, right? And we'll see that how random walk. In fact, in link prediction also we'll discuss random walk with restart and see how this is an effective way of ranking nodes. Now, what would happen after the end of all these iterations, right? When you stop, you will get this R matrix, the final R matrix. So you will see that R of t is very same as R of t minus 1. Therefore, you stopped, right? At 2 subsequent iterations, you haven't seen any change in the values of R. Therefore, you stopped, right? Now, what is this R? R is a matrix, right? R is a matrix of size V cross 1 or 1 cross V, whatever, right? So these numbers, and this also sums up to 1, right? So therefore, this is a probability distribution. Okay. Now this is called stationary distribution. Remember this terminology. This is called stationary distribution. Now, what is stationary distribution? So in this kind of iterative recursive formulation, when you keep updating, so and the limiting condition, right? When the algorithm converges, at the time of convergence, the value that we obtain is called stationary distribution. Okay. So whenever you see any recursive formulation, you may be asked to decide or to conclude whether your formulation has any stationary distribution or not, whether your algorithm will converge or not, right? You'll have to mathematically prove that it would converge. Okay. All right. So now let's look at the advantages and disadvantages of PageRank. The advantage is that you can write everything in terms of metrics, and therefore any vectorized systems can be used to compute PageRank. Okay. It is guaranteed to converge to a unique solution. So it always has a stationary distribution, right? Now PageRank is the PageRank algorithm that we discussed. This is computed on a static graph. So given a static graph, you can run PageRank beforehand, and you can store the values of all PageRank values of all the nodes, right? So you do not need to run PageRank algorithms again and again. So what does it mean? It means that let's assume that there is this search engine, and the rank of the search results are dependent on the PageRank. Let's assume that you have put in some query, and your search engine returns 8 web pages, right? Now, how do you rank these 8 web pages? You can rank it based on PageRank, for example. Now, PageRank is computed beforehand, right? You know the PageRank beforehand, so therefore you don't need to do anything on the fly. Okay, you just identify relevant web pages, and the ranking will be given. Ranking will be obtained from the PageRank. Okay, so you can pre-compute everything. Now, ranks are robust and stable because, remember, it all depends on the in degree of a node, not the out degree. Impact of a node is determined by its in degree, not the out degree. Okay, so in degree is something that is hard to manipulate. So let's assume that you want to manipulate the graph, you want to poison the graph, you want to change the graph so that your page will receive more page rank, right? But you can't do that because it all depends on whether other pages will point to your page or not. So you need to convince other pages to point to you, which is hard. If your page is a fraudulent page, nobody will point to your page, right? So in degree manipulation is very difficult. Out degree manipulation can be possible. You can from your page you can cite, you can refer to any pages. It is your control, on your control, right? But page rank is dependent on in degree solely. So it is robust. It is robust to any manipulation, right? And it also tries to model real world surfing behavior, web surfing behavior. So in that sense, this is more intuitive. Okay. So what are the limitations? The limitations are manifold. The limitations are the page rank also is prone to spamming. What does it mean? It means that let's assume that there is a group of web pages, right? A massive group of web pages. For example, there are thousands of web pages which are connected to each other. Okay, let's say there is this click which are strongly connected to each other, right, and sparsely connected to other nodes, right? So if the random walker somehow comes to this part, this closed group, the random walker keeps moving inside this group because all the nodes are highly connected, right? This is very less likely, very less probability that the random walker will move from this group to any other group, right? So this is again kind of a spider trap, but not totally, because there are some outgoing edges, but the outgoing edges are small in number, less in number. Okay. So and you can easily create this. You can easily create this by paid accounts, right? Say for example, on Twitter, you can easily create say 1,000 such accounts, right? You can also make a group of users with your friends, right? And your friends, keep citing each other, keep following each other, right? And automatically their impact will be boosted. Ultimately, it all depends on the rank. It all depends on the links, right? And links are still prone to manipulation, right? The second problem is that it turns out to be successful metric for static networks. Okay, when it comes to dynamic networks, although there are plenty of research, but dynamic updation of page rank is little difficult, little tricky. So therefore, you may need to recompute page rank periodically. Okay. Right, but the major problem that the major limitation that the page rank suffers from is something called the diversity. Okay, what do you mean by diversity? So remember, when we rank pages using page rank, we only look at degrees. Okay, and we do not look at where these high degree nodes are located. Okay, so let's take an example of this network. Okay, what do you think, like which nodes will have high page rank? If you calculate, you see that page 1, page 3, node 1, node 3 and node 2, these three nodes have high page rank values. Okay, you see here nodes, the size of the nodes indicate the values of the page rank. Larger the size, higher the page rank value. Okay, so these three nodes have high page rank value, followed by this node, and so on, right? So whenever you rank nodes, you will rank these three nodes first. Okay, but what's the problem here? The problem here is that if you look at the context, the network context, okay, these three nodes are located at the same context, meaning that you may not be able to extract diverse information from these 3 pages, because these 3 pages are part of the same kind of cluster, right? They are part of same location in the network, right? Therefore, what would happen eventually is that they would end up conveying the same information, right? Say for example, you know, these are the 3 veg, these are the 3 non-veg restaurants, right? In Delhi, for example. Okay. And let's now why this is a problem. The problem is that when we search for some information, we always look at 2 things. One is called the prestige, other is called the diversity. Okay. What is prestige? Prestige is nothing but the page rank. Okay. How impactful the node is. Now, this prestige can be calculated by page rank, or prestige can also be calculated by simply say degree. What is diversity? Diversity indicates how diverse your results are. Say for example, you are your query is you know, give me the name of show me the restaurants in Delhi where chicken items are favorite, chicken items are famous, let's say. Okay. Or say you know, so let's assume a query that you know, only show those restaurants which are popular in Delhi. Okay, let's assume this query. What would happen if you use PageRank is that you may see that the top 10 restaurants which are returned by the algorithm, if you only use PageRank, it may happen that out of top 10 results, 8 of them are non-veg restaurants. Only 2 restaurants are veg restaurants, which is also obvious because, you know, many cases we have seen that, you know, people generally visit non-veg restaurants. They like, you know, non-veg foods and so on. Therefore, they give more weightage, more, you know, ratings and so on, right? So if your result is not diverse, if your result only populates non-veg restaurants, right? Now let's assume that you want to also look at, you also want to look at some diversity. You are also looking for you know, veg restaurants as well along with non-veg, right? So what would be the ideal ranking in this case? The ideal ranking algorithm should rank few veg restaurants, top veg restaurants, few top non-veg restaurants at the beginning, and then the rest you can arrange accordingly, right? So instead of ranking in this way, right, if you rank so instead of ranking node 1, node 2 and node 3 as top 3 nodes in the rank, if you rank this node 1, then node 4, node 5 at top 3, right, this would be more diverse, because as if when you return this node as the rank result, the entire part of this network will be covered by this node. But this node is a prestigious node, therefore this node may cover the other nodes present here. Okay. Similarly, if you return this node, it also covers some part here. If you return this node, this covers this part here. So then ideal ranking algorithm should also look at the diversity. Now remember, it is not the case that we are compromising on the prestige. We are not, because here you look, you can see that, you know, node 4, node 5, they are also top nodes, right? But they may come after node 1 to 3. So they are also prestigious nodes. But they may not be returned within top 3. Okay. So what I'm trying to say is that we should come up with a rank where 2 factors are equally taken into account. One is prestige, other is called the diversity. Now the point is, how do we capture prestige and diversity together into the metric, into the formulation, into the PageRank formulation, for example. Okay, and this is captured using the rank called DivRank, diversified ranking. Okay, so to understand what is DivRank, diversified ranking, let us first understand random walk process a bit more. Okay, so what I discuss now is something called time homogeneous random walk. What is time homogeneous random walk? Time homogeneous random walk is something that the PageRank follows. Okay, what is it? It basically says that, okay, before that, let's also try to discuss something else. So we have seen that PageRank concept can be easily modeled by the random walk process, right? And what does it say? That you are basically moving from one node to another node with using through certain hyperlink, right? This can also be captured using Markov process. Now I'm not sure whether you know what is Markov process, but generally you assume that Markov process is a, let's assume that it's a finite state automata, right? If you do not know what is automata, let's assume that this is basically, you know, a set of states. Markov process is a set of states, right? And two states are linked using some transition probability. Okay, so let's assume that you have the states. Okay, so let's say so these four states indicate your daily activity. Let's assume that. So this is that you are waking up from bed, right? This is you are going for breakfast, right? This is breakfast. This is you are going to your college, and this is you are taking your lunch, and so on. These are the different states of your daily work, daily life, right? So when you wake up, with certain probability, you go to you go for breakfast, right? And this is very high. For example, the probability is 3/4, right? In some cases, if you wake up late, you may skip your breakfast and you directly go to college, right? This is 1/4. Now after breakfast, you can go to college, right? So let's say this is also very highly likely that this is 3/4, right? It may also happen that you skip college, right? And after breakfast, you stay at the home and you take your lunch. This is 1/4, right? It also happened that after college, right? I mean, during your college, you take your lunch, right? Probability 1. So these are different states, and states are connected through transitions. So these are called transition probabilities. Now Markov process basically, you know, helps you understand that when you are at a particular state, what is the likelihood that you move to another state? What are the decision factors? Whether the decision factors are solely based on, you know, based on the current state or based on the previous other states, and so on and so forth, right? What I'm saying is that this is exactly random walk, right? What we do in random walk, say we are currently at this node, okay, and we decide whether I would move through this link or through this link, right, with certain probability. And so far what we assumed is that there are two factors. One factor is you can either move through this link, or you can directly jump to any node. So from every node there is a teleportation link to all the nodes, right? Again, from this node, teleportation link to all the nodes, and so on. Okay, so PageRank can also be visualized as a Markov process. Okay, now, so this probability, this transition probability from node U to node V. Okay, how do we define it in PageRank? So let's say this is probability of moving from U to V. So probability of moving from U to V are determined by two factors, right? What are the factors? Again, either you, so you are at U, you are at node U, and you are trying to understand the probability to move to V. Okay, and remember, U has other links. Okay, what are the links? We have already mentioned that these forward links are denoted by FU. Okay, so what you do? So in PageRank, if you follow these hyperlinks, the probability would be what? The probability would be 1 by mod of fu, right? Right. So let us define something. So uh, um, so I don't know whether I can erase it, but let me see. So P of uv is right, 1 minus t and d. Okay. Okay, let's assume that is a wuv, okay, by sum of v belongs to fu, okay, w comma p. What is this? So I wrote it in a very generic manner. Okay, you can also write. So I'm assuming that this network is a weighted network. Okay. If it is unweighted network, then it's very simple. Okay, so let's assume that it's a weighted network. So weighted network means that each of these edges has some weights, right? So this weight is w of u comma v. So say this is b. Say this is x. So this is w u comma x, right? So this factor, which I earlier wrote 1 by fu, I assumed that it is unweighted, therefore 1 by fu. But if this is weighted, then w of so then the total weight of outgoing edges of u is this one. Look at it. fu is the all forward nodes, right? Total weight would be this one. So total weight and how much is contributed for this node v? This is wuv. Now in the unweighted case, if everything is same, if everything is 1, then this is simply 1 by fu. Okay, so this is this factor. So along with this, we also consider another factor, which is called prior, right? We write it as p star v. You see here, this is also parameterized by d and 1 minus d. What is this prior? What is prior? Tell me. What is prior? This prior is nothing but the teleportation probability that I mentioned earlier. Okay. So there are two factors, as I mentioned earlier. There are two factors. One is either you move through hyperlink or you jump through teleportation probability. Now P star V is the prior impact of node V. Prior impact can be uniform, 1 by n for all the nodes, which you considered earlier. But I'm trying to write it in a generic manner. It may happen that I want to give more weightage to certain nodes and less weightage to certain nodes, because I know that these restaurants are more impactful compared to these restaurants, for example. Okay, so when you are at node u, please try to understand, when you are at node u and you want to measure the probability of moving from u to v, what are the decision factors? The first decision factor is the prior probability of v, how impactful v is, which can be 1 by n in case of PageRank, and the proportionate probability that you want to compute from u, and the proportion comes from the outward link of u. So this is the probability. Okay, and I write this as p0. Why I am writing at p in p0? Because this probability doesn't change in case of PageRank. right? Because it depends on the static network structure, and this is fixed, right? This is fixed, so this probability will also be fixed. So the transition probability from one node to another node is always fixed in case of PageRank, right? Now, in case of DivRank, I'm changing something. Okay, what I'm changing now, what I'm saying is that I define something called time heterogeneous random walk. I define something called time heterogeneous random walk, right? And this is also called as Vertex reinforced random walk. Okay, I'll discuss what is this. This is time heterogeneous random walk or Vertex reinforced random walk. What does it mean? It means that the transition probability now, right? Transition probability from U to V is not static. It will change over time. Okay, it will change over time, and the change is reinforced by V's current prestige. What I'm saying is again as follows. What I'm saying is that if I want to rank, so basically the intuition is as follows. The intuition is that if a particular restaurant is visited by many people, right, automatically it would get more attraction and attract more people. It is similar to rich gets richer. If a place is visited by if a place starts attracting many people, next time also it will attract many people. So if we start at the very beginning, if we assume that all these probabilities are equally likely, all these probabilities are static, not equally likely, static, right? But as soon as you move from node U to node V, for example, again from V to W, from again W to V, from again V to S, again S to V. So what is happening? You keep hello, can you hear me? You keep can you hear me, guys?
Yes, sir.
Yeah, so what is happening is that, so let's assume that you are doing random walk process. Okay, node U to V to W to X to V, S. So and you see that node V is something which is encountered again and again. If node V is encountered again and again, it means that the transition from U to V, the transition from W to V, the transition from S to V, all these probabilities is now reinforced by V's visits. The more V is visited, the more the probability to V from other nodes to V will increase. Okay, so a simple formulation is this one. So the probability at time t, the probability of moving from U to V is the probability at time 0 is proportional to probability of at time 0 and the visiting probability of V at time t. The more you visit node V at time t, the transition probability from other nodes to V will keep increasing. Okay, now try to understand what is the implication of this. The implication is that, let's assume that your random walk process is here. Your random walker is here at this node. Next time what would happen? Next time this from this node, you say you may move to this node. Okay, automatically the prestige, automatically the transition probability value of this edge will increase. Okay, say for example in the next stage you move here, right? This will increase. Again you move from here to here, this path will increase. What is happening here? Try to understand. What is happening here is that there are two things happening. One is something called collaboration and something called competition. DivRank, what DivRank does, DivRank lets the node compete with each other, right? So there are three nodes highly connected. Okay, what this node will try to attract prestige from other nodes. Okay, the more you visit this node, the more the probability will increase. So what happens is that over time, this node would start, you start getting more important from the other nodes, and it starts getting richer and richer over time. There is always a competition happening between nodes, right? And over time, the more the visit, the more the attractiveness and more the prestige. Okay, therefore, if you are located within a circle where all, most of your nodes are, most of your friends are kind of same caliber, what would happen is that eventually only one or two of your friends will win, and other becomes poor. Okay, so therefore you see that if you use div rank, you see here only this node will win and other two nodes will become poor. Similarly here, this node will win, other nodes around the given node will become poor. Similarly here, therefore this will be returned, this will be returned. So what the essence is that if nodes of similar importance, of similar prestige are connected to each other, it is not possible that all nodes will win. Only a few nodes will win at the end, because over and over the iteration, what would happen is that you start squeezing, you start taking prestige from your neighbors, and you start becoming richer through vertex reinforced random walk. This is the intuition. Okay, so let me now proceed with the formulation. The formulation, so if you understand the intuition, the formulation is very clear, very straightforward. Okay, so now, so we have earlier seen that in case of page rank, this was simple P of 0, U comma V, 1 minus D prior, right, plus D, something like W U comma V by sum of all B belonging to forward of U, right, W U comma B. This was there, right? And if you look at the components, none of these components are time dependent. So now in case of div rank, this is the formulation. D and 1 minus D remains same. The first part remains same. The second part is important. Second part, so now what is happening is that, so what you are doing, you are checking the probability from U to V. Okay, now this probability you see here, what is this? This is essentially, you can write it as P of, right, I would say this I would say this is T plus 1, and this is P of T, right, U V. This is proportional, not exactly true, this is proportional. I mentioned earlier, right, that this one. Okay, so the initial probability of U to V, right, initial probability of moving from U to V times the current visit of V, and this is divided by, this is normalized by the sum. So meaning that, let me draw it. This is U, this is V, say this is X, this is Y, this is Z. Okay, so P of T U V is, first part is simple, second part is D, P of 0 U V in T of V by P of 0 Ux in Tx plus P of 0 UV in TV plus P of 0 U Y in Ty plus P of 0 U comma Z in Tz. Okay, so this transition, you basically take the sum here also, right? And you see the proportion of node V from this sum. Okay, so now this is your PTV, or PT plus 1, whatever. Okay, so sorry, so this is your PT U comma V. Now this is the transition probability, right? Now from transition probability, now tell me, it's very simple. From transition probability, how do we get the div rank value of a node? So what you are interested in? You are interested in measuring the div rank value of this node V at time t. Now this is simple, because now since you know the transition probability, say this is node A, node B, node C, these three nodes are pointing to V, and you know P of t minus 1 A comma V, P of t minus 1 B comma V, P of t minus 1 C comma V. Okay, so the prestige of node V at time t is what? Prestige of node A at time t minus 1 times this one, plus prestige of node B at time t minus 1 times this one, plus prestige of this times this. This is one component, which is this one, and V itself has some prestige, prior probability. So this is the prestige of V at time t plus 1. Now this prestige at time t plus 1 will be used at time t plus 2. So transition probabilities are time dependent, therefore which would again lead to make the importance of nodes time dependent, and so on and so forth. Right? Now this is the simple yet very effective modification on PageRank, and this has led to a diverse ranking. Okay, so div rank considers the impact, the prestige and diversity together, along with during ranking process, where PageRank only considers the prestige. Okay.